right, this will be the overview video for chapter 20. So we're going to briefly go through electrochemistry, which has to do with current and voltage and really the transfer of electrons in a chemical reaction. We're going to revisit redox reactions and go over a few key equations relating voltage and electron transfer gradients to Gibbs free energy, like we learned in the previous chapters. All right, so lightning. So lightning and batteries, I mean, they operate with the same electromotive forces, meaning electrons are transferred and charges from negative to positive, the electrons move. So lightning actually occurs from, you have to see you have a cloud, right? And then you have water vapor is in the cloud. Now, the water vapor that's lighter will go to the top of the cloud and it will start to condense. When it condenses into little ice particles, that will be heavy enough to come down. And the bombardment of these lighter hail ice particles from the top of the cloud bombarding with the water vapor particles that are coming up into the cloud, or up higher up in the cloud, they hit each other, and this hitting causes a transfer of electrons. So what that causes is on the bottom of the clouds a negative charge, and on the top of the cloud is more of a positive charge, meaning a lack of electrons. So the increasingly negative charge towards the bottom of the cloud eventually reaches a point to where it's so negative and so charged that it has to discharge into the nearest positive source, which is the air. And then it discharges into the air and it makes lightning. But we'll talk more about that in class. So all in our chemistry context, this transfer of electrons relates to oxidation reduction, which is, we call them redox, which you have an oxidation half reaction and a reduction half reaction. The oxidation, remember from oil rig, oxidation is losing electrons and reduction is gaining electrons. That's going to be very important going forward. So we have our half reactions. We've seen these before, where oxidation half reaction means your electrons are being released. So oxidation is losing. So they're losing electron. Iodine is being oxidized, meaning it gains oxygen, loses hydrogen, but all the time it loses electrons. That's very important in this chapter's context to understand the definition of oxidation and reduction, not just from an oxidation number standpoint, like we talked about in Chem 1. But for oxidation, we're talking about an increase in oxygen atoms or an increase in hydrogen atoms, a decrease in hydrogen atoms, and most definitely a releasing of electrons. And reduction is going to be the opposite. It's going to be a loss of oxygen or a gain of hydrogen. And the oxidation number will decrease. And electrons are going to be added. So reduction is gaining, meaning there'll be gained electrons. So we can balance these redox reactions. So balancing redox reactions is a little bit different than balancing our normal reactions. So first we need to assign oxidation states, determine what's being oxidized and what's being reduced. Then we need to write our oxidation and reduction half reactions. We need to balance them by adding hydrogen or oxygen in the form of water, then adding hydrogen, and then if it's in a basic solution, we neutralize it with OH, but that'll be specified. Then we need to balance the charges by multiplying it, and then we got to add them up. There's a lot of things involved. We're really going to talk about this during lecture, but and we'll go over specific examples, not in the overview video. And there'll be other videos dedicated to these examples. It's the same process every time. It's not too hard. Here's some examples. Electrical current, we measure it in amps. So it's the amount of electrons per second that kind of go through a conductor. So that's what our current is. So current is in amps. So a number of electrons per second through a system. And 1 amp is 6.242 times 10 to the 18th electrons per second. And 1 amp is a coulomb of charge. So those are some key definitions that are good to know for some of the homework problems. And then a volt. So we're going to be measuring our redox reaction potentials in volts. So 1 volt is a joule of energy per coulomb of charge. So how much energy does the coulomb of charge give in this system, in this reaction system? And that's measured based on the potential difference. So the larger the potential difference means there's more volts, means there's more energy in that battery or in that voltaic cell or in that electrolytic cell. And it's all governed by these electromotive forces, EMFs. And we have a standard EMF, which can be calculated as our cell potential. And we also have electrodes, which are involved in this galvanic cell. And we'll talk about that once we see them. We have anodes and cathodes. We've seen these words before. An anode is where something's being oxidized. So the way I remember it is the vowels are paired with vowels. So anode, oxidation. Cathode, reduction. So consonants, C and R are consonants. Meanwhile, A and O are vowels. That's how I remember it. And the anode is where oxidation occurs, meaning they're losing electrons, meaning they have electrons to start out with. So originally, they're more negative. And then the cathode, because originally is more positive, because the electrons are going to flow from negative to positive or from anode to cathode. And then there's this thing called the salt bridge, which we'll see in the next, in this voltaic cell. So I'm going to be using terms like voltaic and galvanic. So voltaic and a galvanic cell are the same thing. And that just means they happen spontaneously. And we'll talk about another type of cell called electrolytic, which is a little bit different. It kind of goes the opposite direction and it needs energy. So these reactions, though, the voltaic or galvanic cells are spontaneous, meaning they happen without any external energy. And which also means their Gibbs free energy is less than 0, or it's negative. So here we have our anodes on the left side. And here's a standard notation. So anode is always going to be on the left. Cathode is always going to be on the right. So here the salt bridge is just to allow ions to pass through. I mean, it just, so no charge builds up on either side. And then you have a wire, which the electrons will flow through in order to power a source. So what else do we have going on here? Oxidation, we see that there's a losing electrons in the zinc and a gaining of electrons in the copper. So cell notation, we usually have single and these double lines. So single line means a phase barrier. So if you have two species that are the same and they have different phases, let's say one of them is a solid, one of them is a liquid, you denote their differences by one solid line. A double line means a salt bridge, and usually it's the oxidations on the left, reductions on the right. So anode is on the left, cathode on the right. So it goes anode, cathode in the same notation that it is shown in the diagram. So here we have on the left side, on the anode side, we have iron is being oxidized to iron 2+. And that's going to be, you have Fe, single barrier, which means Fe solid, single barrier, Fe2+ aqueous, meaning that's the oxidation that occurs. Then we have our double line, which means we have a salt bridge. And then on the reduction side, we have the permanganate ion, manganese 2+. And then we have hydrogen. And then we have platinum as the cathode metal. And what we have here is during this current, during this galvanic cell electron motion, what's going to happen is if the metal is reduced, what's going to happen is it's going to precipitate because it goes from manganese 2+ to manganese. So on this cathode side, what will happen over time is the manganese 2+ will turn to manganese solid. And what will happen is it'll start to create solid crystals on the cathode platinum. That happens a lot, but in this case specifically, it's not going to happen. But usually the metal that is being reduced is going to form a solid. So for this specific example, not too much. It doesn't really happen because it goes from +7 to +2. But a lot of the times they get reduced from, let's say, +2 to 0. In that case, they form crystallized solids. So we have the standard hydrogen electrode, which it has an it has a voltage of 0. So it has a 0 potential difference. That's where we use our standard. And basically, we're going to get to the point of if you have different half reactions, all of these half reactions have a reduction potential. That's going to be a key thing in this chapter, is reduction potential. And we'll go to the table of reduction potentials. Here they are. Now, this is going to be our guide for a lot of the questions in order to figure out the voltage of a galvanic cell by subtracting the two. But it's easy to do, but don't try to do too much. So think about it in very simplistic terms. You have all of these equations listed are reduction. They're reduction. So this means this E naught is the standard reduction potential in volts. The higher the standard reduction potential, the more likely it is to be reduced. Right? Very easy. The higher meaning the more positive, not absolute value. Take the numbers for what they are. They are reduction potentials. So if it's higher, more likely to be reduced. If it's lower, like these that are negative, the less likely it is to be reduced, the more likely it is to be oxidized. I'll stress that more in lecture, but let's say we can flip the sign to get our oxidation potential. So if we have, which we're not going to use too much, but let's say we have aluminum 3+ to aluminum solid minus 1.66. That's the reduction potential. Not very likely to be reduced, but its oxidation potential is plus 1.66. And that's pretty easily oxidized, meaning it's easily dissolved, right? It goes from solid into aqueous. I'll talk about dissolving soon. So the way to figure out the voltage of one of these galvanic cell systems is you simply do the cathode minus the anode, right? And this is for reduction potentials. So you do the reduction of what's being reduced minus the reduction of what's being oxidized. And since the reduction of what's being reduced should or is all the time greater, you cannot have a voltage that's negative. They're all positive. If you did a negative, that means you switched the sign, you did something wrong. So for example, if we have iron and aluminum, iron, this one right here, Fe2 plus to Fe, it has a reduction potential of negative 0.45. Aluminum is negative 1.66. Therefore, iron will be reduced. So it'll be negative 0.45 minus negative 1.66. And therefore, your answer will be positive all the time. So just take the numbers for what they are as reduction potentials. Okay, let's continue. So the idea here is that because we're going by this list of the reduction potentials, and we can tell which one's going to be oxidized and which one's going to be reduced by these standard reduction potentials, we can say that it's a spontaneous reaction if it went in the way that we wanted it to go by the chart, meaning the one with the higher reduction potential will be reduced, the one with the lower reduction potential will be oxidized. That is a spontaneous reaction. If we flip it and go the other way, it's not spontaneous. So you can see that here. And if we flip it and go the other way, we need energy for it to happen. That's called an electrolytic cell, which we'll see later. So another skill that we're going to learn is how to predict whether a metal will dissolve in acid. And it's very easy. We're just comparing these reduction potentials. So basically, for a metal to dissolve, that means it's a solid and it becomes oxidized into a +1, +2, +3, or whatever. It goes from solid to plus and aqueous. Here you see that here for zinc. So zinc goes from solid to +2 and it becomes aqueous. That is what we call dissolving. It's another way of thinking about it. And we can compare that to the standard reduction potential of of hydrogen, which is 0. So for things like HCl, which is just hydrogen's involved, chlorine is just a negative charge. What happens is if your reduction potential is greater than that, less than that, less than 0, that means whatever it is, hydrochloric acid is going to dissolve that metal, because it will then become, that metal is lower reduction potential, therefore it will be a higher oxidation potential. So it's more likely to be oxidized. There's other types of acids we know is like HNO3, nitric acid. Nitric acid acts a little bit differently because once this dissolves in water, the hydrogen is free, but we also have NO3 minus, which itself is reduced further. And here's the reduction for that. So NO3 minus plus 4H plus 3E, 3 electrons equal NO plus 2H2O. That's the reduction for NO3. Since that reduces further, it has its own potential, which its reduction potential is higher than 0. And most of the metals are below it. That means most of the metals will dissolve in nitric acid. So you can work on that. Then we can talk about it for, we talk about delta G. So spontaneous, now we know delta G is negative. Delta E is positive for spontaneous. We just learned that. And also K is greater than 1. That means the reaction will occur in the spontaneously in the forward direction. And then we have this another equation where we can quantify delta G in terms of E by using negative N, which is the number of electrons, times your F, which is Faraday's constant, times your voltage of your cell. So that's a useful equation on the homeworks. And here's some other useful equations. We'll go over them in class that will be given. And another one, here's the Nernst equation. That's a good one to know, where you can find the voltage from the number of electrons and the value of K, which is the equilibrium constant. And here's just the same equations. The Nernst equation, they go over that. So here's that. Different types of batteries. So you have the dry cell battery, which is a galvanic cell. And there's different components of it. You have the manganese oxide is reduced, and the zinc is going to be oxidized. So, and is in positive and negative end. Electrons go from negative to positive, and that creates a cell voltage, which can then power a source. So this specific battery, this alkaline zinc battery, does not have actual battery acid. I mean, it does have, the battery acid is technically a base. I mean, KOH is a strong base, and strong bases will still burn you like acids will. But our traditional battery acid is sulfuric acid in a lead battery. So here are those types. So here's a lead battery, and you see it has sulfuric acid. There's zinc cadmium batteries. Then there's these rechargeable batteries that are made of zinc, also lithium ion batteries. I'm sure we've heard of them. Fuel cells, where we'll be talking in brief about these. It's not that important to exams, but you can take a look at other research if you want. You can do research on your own and learn more about how they work. There's a ton of YouTube videos out there. And then electrolysis. So now we are going to pay attention again. And electrolysis occurs in an electrolytic cell. And it's a process that is non-spontaneous. So far we talked about galvanic cells, which are also called voltaic cells. And they are spontaneous, meaning the oxidation and the reduction happens spontaneously by itself without any external energy. But electrolysis is going to use an electrochemical gradient to power something from using an external power source. So it goes against the grain, in other words. So a voltaic cell, we have this, the spontaneous reduction of copper and the spontaneous oxidation of zinc. It happens based on the differences in voltages of the reduction potentials of zinc and copper. Whereas electrolytic cells, you see how it's flipped. The cathode is now the zinc, and the zinc is being reduced. Whereas the anode is now the copper, and the copper is being oxidized. How the hell does that happen? The electrons are going to go the other way, right? From anode to cathode. Yeah, but what we need to do is we need to supply an energy source, or else this can't happen. Otherwise, nothing will go on. The zinc wants to be reduced, or sorry, wants to be oxidized. but we're forcing it to be reduced. The only way to do that is adding energy from, in this case, a voltage source. So here's the differences of that. Some electrolytic reactions require more voltage, and we call more voltage than the equations predict. And this is where we see our DC power supply. So every time we need like any device that needs a DC power supply that plugs into the wall, it has electrolytic cells in it for it to power. So you need external energy. Electrolysis of NaCl. You can use it to mix or to separate compounds. And then the rest of it is not really too important about, it's more specific types of cells. Stoichiometry of electrolysis. It's kind of basic. Where, I mean, if you have this reaction, this reduction of silver, how many moles of electrons must pass through an electrolytic cell for silver plating in order to plate 3 moles of silver? Well, it's 1 electron per atom. So it would be 3 moles of electrons for 3 moles of silver. That's what we mean by stoichiometry, is that we can say our electrons are stoichiometrically, the ratios are compatible with that of the atoms. So we can use the same math we've always been doing. Corrosion can happen of metals, and usually it's by oxidation reduction reactions, redox. And the most common example is iron rusting. So where iron becomes iron oxide. And here's a diagram of that. We'll go over that in class. So we have water. When water touches iron, immediately oxidation will occur. But if you have prolonged exposure of iron to water, let's say rain and the elements, what will happen is the iron will be transformed and reduced to, or oxidized, to iron oxide. And then the iron oxide will become aqueous, and it will be stripped away from the solid iron. And it will leave back this kind of rust, which is the iron oxide, and it's hydrated with water. So there's different ways to prevent rusting. I mean, you can put paint, some anti-rust paint, make it more. So if you attach a lower reduction potential metal, meaning it's more likely to be oxidized, that will stop the iron from being oxidized. And then that's about it. So stay tuned for the full video it's going to be posted within the next couple of days, and be sure to like and subscribe.